Hi everyone, this is Gloria Fluxa, Marketing Director at Submer, and here I am together with Jon Summers, who is the Scientific Lead in Datacenters at the ICE Data Center and at the Research Institutes of Sweden, RISE.
Thank you.
And Natalie Cruchet, who is our Head of ESG and Sustainability at Submer, Mark Miyoshi, who is the R&D Director, and Peter, who is the VP of Fluids and Chemistry. Thank you everyone for coming, and thank you, Jon. We're here with Jon Summers, who is the research lead at RISE, research in Institute of Sweden.
It's institutes, yeah. It's more than one institute put together. Yeah.
It's more than one.
So it's got the plural institutes, yeah.
Okay.
Yeah.
And well, first of all, thank you very much for coming. We know you have a busy schedule. But we wanted to hear more about the RISE deployment with immersion cooling that you have on your premises. Can you tell us a little bit?
Okay, yeah. I mean, this is an interesting story, and it can. So effectively, I mean, as a research institute, we get invited to these competitive funded projects, and this was a Horizon 2020 project. So it's funded by the EU to look at renewable sources of energy for district heating. And they wanted to build some proof of concepts, different ways of generating heat for district heating. And we got invited to the project, and we thought, well, what can we bring to the project that ticks the boxes of innovation? It has to be innovative, and that's the way you get the funding. So we decided that just using standard IT equipment with a heat pump has been done. It's not innovative enough to get the funding. So we thought what we could do is let's use immersion. Let's use a form of liquid cooling to start with, because that's a disruptive technology. It's not an old technology. It's not a young technology. It's an old technology. It's been around since the 50s. Liquid cooling. It's quite interesting to look at the history of liquid cooling. But the idea here was to use that as the primary point of heat generation, and to combine it with another source of energy generation, which was on-site power generation using solid oxide fuel cells. These are high-temperature fuel cells, so internally they're running at 750 degrees centigrade in order to produce electricity and heat. So the electricity was driving the smart pod, which had the servers in it, repurposed OCP servers. And then the heat from the immersion system was then used to preheat the air to the fuel cells, because the fuel cells need three things. They need water, fuel, and air. But when you're deploying this in a very cold climate in the north of Sweden, where the temperatures can get down to minus 25 centigrade outside, you don't want to bring in really cold air. So you want to warm that air up, and that's why So the whole idea was to run this as a proof of concept. And then the third and final part of that was to then, the heat that's generated by the fuel cells was to connect it to the district heating network. So then the whole cycle was complete. The question is now, what fuel were we using? Well, the original concept was to use hydrogen, and to use green hydrogen if you can get your hands on it. But it's actually very challenging using hydrogen. So what we went with, it was a locally produced biogas. And it's produced 30 kilometers away from where we were stationed. And it's made from organic waste and wastewater in anaerobic digesters. So they're taking nearly 10,000 tons of waste food a year and wastewater from the sewage networks to produce biogas. And that biogas is not raw gas. It was 97% methane. So we were able to use that as the fuel into the fuel cells. And of course, the high temperature in the fuel cells strips the hydrogen off through using the steam reforming process. And so you have the hydrogen, which then runs it like a battery. It's the same electrochemistry that you get in a battery. And that generated the power to run the immersion tank. So why immersion? Why did we choose immersion? And I think, we wanted something that was really robust outside, because it was in a container that was going to see quite extreme temperatures. And we thought the thing about immersion is that you've got all of the microelectronics in contact with the liquid. You're harvesting all the heat from every single component. So that's one of the reasons why we thought that kind of technology would be a good fit for this. Yeah. Secondly, I was very aware that I wanted a system that didn't move the hydrocarbon, the dielectric, too much. And of course, that there are systems on the market that move the hydrocarbon too much, and you get this oxidization. There are also those that rely on natural convection, and I knew that has its challenges as well. So it was something that slowly moved the coolant around, and that was what was in the procurement requirements for the immersion system, and that's why we ended up with a Submer smart pod as the primary source for to house all the open compute equipment.
So if I understand this correctly, the main purpose was immersion cooling to be the vehicle to heat reuse.
Yes.
That's amazing.
Yes. It was more of a data center concept. So going a step further is that this is not, with fuel cells, it's not deployable at really large scale. Mm-hmm. We're talking about deploying something in an urban area where you have stress on the power grid already, because you've got other consumers of electricity. You don't want anything that's too noisy. So you don't want spinning fans or huge amounts of, from the components, compressors or anything like that. So, but also it's going to be close to in an urban environment. You've got a great case for heat reuse, because there's a heat demand in an urban area. So that's the whole idea, was to look at an edge style deployment that was not putting any stress on the power grid, was quiet, and
people could benefit from the
from the heat reuse as well.
A lot of check boxes.
It was a fantastic project. It's still going on, but the proof of concept has ended now. We've run for 14 months, 15 months with the smart pod, and it's seen external temperatures of -25 and +25 outside. So
what do you think of that, colleagues?
What are the preliminary results? Can you delve into that a little bit?
So the preliminary results, I think we can say that with a outside temperature of -25, we can get 65 degrees out of the system.
Got it.
And that's because you can't get 65 degrees directly from the immersion system, but the combination with the fuel cells, you can get 65 degrees centigrade. The district heating network supply temperature when it's -25 outside is at 115 degrees centigrade. So we had a mismatch there. So which meant you can't really put 65 degrees into 115 degrees.
You still need a heat pump.
So no, we didn't. What we did is we said, well, let's look at this a different way, because the district heating, which was coming from the streets, it's a huge network in the north of Sweden, in Luleå. There is a secondary network which supplies heat to the building. It's a very large building, but that secondary loop was running at a much lower temperature.
Got it.
So why don't we cut into the secondary loop, relieve the stress on the primary loop, and we're still helping the system by providing the heat to the secondary loop. So that's how we got around that problem. Engineering is all about compromise. We're always compromising. You can never do what you exactly want to do. And that's the great thing about engineering, I think, because it's always challenging us from, I'm sure you have this, problem solving. It really exercises those problem solving skills.
Absolutely. Definitely. Now, when it was 25 degrees Celsius outside, were you still using the fuel cell as the primary source of cooling, or did you have dry coolers or something like that?
That's a good question. So the thing is that the heating network was always on. Because this is where it gets more challenging, because does this translate to, say, Barcelona? Because, do you have any demand for heat when it's 30 degrees outside? Right. You probably do have to generate hot water. You still need it for hospitals, laundries, schools. You still need hot water. So there's still a demand for hot water. But it's much less than in the winter. But we did have challenges in the summer because everything was running too hot. Because you didn't really need to heat up the air,
Right.
and so we couldn't really reject the heat to the system that had the fuel cells because it was already too hot.
Yeah.
So we had to reject it to a dry cooler.
Okay.
And of course, a dry cooler was always in the loop because it acts as a buffer. Because if you've got too much heat from the immersion tank, you need to have a release for that.
So you didn't have a diverter valve; it was always going through the dry cooler, no matter what.
There was a diverter valve. Yeah, we had which was a little bit controlled by temperature. Yeah, so how hot is the fuel cell container? And these containers were stacked on top of each other. Yeah.
Right.
And we were able to divert the heat depending on a control strategy. Yeah. The other interesting thing about the setup was that a little bit away from the thermals, but to do with the power, is we didn't have electrical storage in the loop. And the problem is that so what we were trying to do is the fuel cells were tracking what the data center required in terms of power requirement. And of course, as the workload started to increase, the power draw from the system increased. The fuel cells were then asked to produce more power, but they're very slow.
Right.
So they were underproducing. And so we were grid parallel because we were connected to the grid.
Yeah.
We could pull power off the grid just to fill in that little gap. Of course, then the workload dropped and the fuel cells were overproducing. So we were sending power back up to the grid. So there was with a battery in the loop, it acts as it acts as an electrical buffer. So it buffers that would have helped.
Interesting. So given all of that, do you think that this is a viable technology or setup going forward?
Absolutely, yeah. I mean, this was an excellent example for using immersion cooling in a quite a challenging environment, I think, because I don't think you would have been able to do this so easily with air or with the direct-to-chip. It was definitely, this particular proof of concept really required immersion cooling. It was a great...
Now, why couldn't you do it direct-to-chip? I think I know that you're...
I think, it's a good, why couldn't you? I think the problem really is that, the issue of the fact that you can only get 75%, 80% of the heat into liquid. You still need to have some kind of air cooling.
And the thermal shock.
And in a containerized system, then you need to then condition that air when you bring it in from outside.
Sure.
Of course, we might have benefited from actually having air exchange inside the container with the smart pod.
Yeah.
Because what we didn't do is we didn't exchange the air in the smart pod. So what we did see, when it's minus 25 outside, the walls to the container are really cold on the inside. And so you get condensation. And that condensation actually had some of the hydrocarbon in it as well. So you run your finger down the cold wall, and so we really needed to exchange the air inside there. I think it needed, and maybe if you were going to exchange the air, maybe a direct-to-chip solution might have been just as good. But still, you're still bringing in outside air, and you still need to warm that air somehow if it's minus 25.
Yeah.
I mean, the Open Compute project does it in a specific way for air cooling, but
when you're dealing with 25 or negative 25C ambient, you do have condensation issues, right?
Yeah.
And condensation issues when they occur near the CPU, that can be an issue.
Exactly.
Obviously, so that'd be another factor.
Yeah.
The thermal shock. I think we were talking about this earlier, but
indeed, yeah.
In the smart pod, all the hardware is in this big vat of fluid.
Yes.
Which gives you that buffer.
It does, and it was, and I think that's why I think when we thought about this long and hard, how do we design this system? I mean, we proposed the project, and then we realized, it's got funded. Now we need to actually build it. That's the challenging part. And so we thought long and hard about this, and it had to be an immersion solution. I think we argued everything else out of the loop. And it's quiet.
Yeah.
Because you still need some fans, even in a direct-to-chip solution. You still need to move the air with some fans. With an immersion system, you don't. It's all, as you know, it's all pumping fluids. Yeah, it's much quieter. Yeah,
absolutely.
So far, I think 98% of the energy that's going into a data center is just evaporated in air. So how do you see heat reuse in the future in Europe? Do you see a lot of pressure? What do you think the data center and industry answer is to that?
Yeah, I think the data centers themselves don't want to deal with heat. I mean, it's a nuisance. I mean, if you think about what a data center has to do, it has to produce, put in equipment that produces digital services. The first problem they encounter is we need to do thermal management. We need to manage the heat, and of course that's where the challenge comes from. And I think everybody sees this as because there's nothing coming out of the data center other than binary digits, ones and zeros or digital information. The focus is quite strong now on the fact that these are demanding so much energy consumption. They draw so much energy off the grid, but they don't actually do anything tangible. I mean, this is why we have this sort of kind of disconnect. I think it was a classic example of people don't understand data centers because there was a government statement. I think somebody was asked, or somebody said in the government, we don't need data centers, you can put everything on the cloud. They completely missed the point of the data center, but I think legislation in Europe is leading the way on this because they see that, wait a minute, you've got something here that's producing a lot of heat, waste heat. I mean, a lot of our fossil fuels go into producing heat, much more than the fossil fuels that the data center industry consume itself. So we need to displace that somehow. And so I think it makes a lot of sense to try and reuse the heat at the same time. But the problem is that I think with heat reuse is that, demand is here for heat and production is here. And then suddenly it's like this, where production is here and demand is here. So you never have these they're never aligned. So you need some kind of seasonal storage. So there are some technical challenges. I think you need to be able to store heat for long periods of time and then release it when you need it. And to try and do it dynamically, I don't think is totally possible. But I think the legislator, through the Energy Efficiency Directive, which you're probably aware of, they're talking about mandating that data centers look at heat reuse. And if it isn't technically or economically feasible, then obviously you don't do it. But to actually, that's the first point of call, is to consider it, to make sure that you can integrate it within any new data center build out. Of course, it's interesting when you talk to data center operators in Iceland, for example, and they say, okay, we're going to have to reuse the heat from data centers. Why? We already have huge amounts of heat. We've got too much heat already from their heat networks, from the geothermal. So it's not a one size fits all. It has to be considered very, very measured, in a measured way. And it's a conversation piece, I think. And it's a collaboration. I don't think data centers can do this all on their own. It definitely needs the suppliers like Submer, but it also needs the energy provider in the loop as well. So those that run the district heating networks, those that run the power networks need to be involved in this as well. Do you not agree? Yeah.
I mean, hopefully in the future is sustainability as a service, so it's not about immersion it's about a lot of things that the data centers, hopefully not the future, but as soon as possible, they make sense. Our tagline, for example, is Submer data centers that make sense. And it's not just about immersion cooling, it's about our way of creating or helping others to have more sustainable and more efficient data centers, right?
Exactly, yeah. I mean, you have a strong argument piece with immersion because, you can reduce the amount of infrastructure that you need to put in. You don't really need to use any refrigeration system. In most geographical locations, you can reject the heat but the better thing is to obviously not just throw the heat into the environment, but to actually try and reuse it. It's a good initiative. I think it's a good push. Whether it really does happen, because there have been so many cases of planning permission for data centers. You must be ready for heat reuse. And so the data center has been built with 2 pipes on the side of the data center and nothing to connect to.
So they're future-proofing the data center.
It, but then there's nothing to connect to it. And there's a case with Telehouse in London, I don't know which Telehouse it is, where there's 2 pipes ready to connect. And then they built a block of flats across the road and never connected them. Because they were well insulated, they were using small heat pumps. It was a much more energy efficient solution than trying to connect all this together. So it's a really, this is engineering at its best, because it really requires joined up thinking. It needs everything to work in a holistic fashion. Yeah, you can't just do these things bit by bit. You have to think about the big picture, I think. Yeah.
A lot of expertise in just one solution, because, engineers and of course Natalie on a sustainable piece, but also Peter, which is our doctor in fluids and VP of fluids and chemicals here at Submer. We're also as a team really involved, for example, in the OCP community. And you need all of these expertise combined, no? Like temperatures of the fluid, yes, temperatures of the water loop, the heat exchangers, or whatever it is that you need in the whole loop, yeah, to obtain all these either sustainable goals or cost goals or efficient goals in general, yeah, on terms of usage of resources, right?
Exactly, yeah. I mean, that's I think materials are key in this as well, because, I mean, we focus a lot on the energy consumption of data centers, but we sometimes forget that it's made up of a lot of materials that go into data centers. You know, the fluids, and also all of the critical raw materials that end up in the microelectronics as well. And this is something that we need to consider when we build this out, to look at it as a whole, in the whole system. You know, and that's a challenge, and he's collecting a lot of data and data that we can trust as well. Yeah,
totally.
Yeah. Well, I like the headline of converting or changing the problem into a solution with heat, which is a problem for all the data centers, into something that you can use, like power that you use. I really love that concept. You mentioned before when we were prepping and stuff, the initiative of Greenpeace, I think it was on 2011, about how dirty is your data, which I loved, by the way. It's a really critical question, a really challenging question. Yeah. And at the end of the day, it's in a critical point of view, how can we change this, no? Or how can people be a little bit more conscious on, the cloud, no? You say with the governments, but the cloud is not a cloud. There's somewhere physical. There's an infrastructure behind it. So
exactly.
It's really important that we're also self-critical with our own industry to change things.
And I think that Greenpeace article that you mentioned, "How Dirty Is Your Data," I think was basically the sequel to getting this industry, the data center industry, a little bit more transparent. Yeah, because it was focused a lot on the hyperscalers. At the time they sort of mentioned the Microsofts, the Googles, and all that. So, and how much the energy and the carbon intensity of this energy that they're consuming. So, I think. And because it was a very secretive industry up to that point, I think it helped to make it a little bit more transparent. I still think, it's not many people have been inside a data center, one of these large-scale data centers, to really see how these things look from the inside. Because you'd be surprised at the scale of the operations of these things. It's quite small. Like our experiment, our proof of concept was rather small. I mean, but these 100 megawatts style data centers are significant engineering pieces. Yeah, but and I think one of the things that it did incentivize is the OCP in a sense as well, because the Open Compute project, being open about things, I think, is, and creating open standards so that it's accessible for everybody, makes a lot of sense, So because at the end of the day, we need to have that standardization, and so that we're talking about the same thing all the time, or we're measuring things in the same way. So we can do these comparisons, Because PUE, for example, when we do a comparison with this power usage effectiveness, it's self-proclaimed. And most data centers say, yes, I have a low PUE, and therefore I'm sustainable. But it's a very small part of the whole story, and it's self-proclaimed. How do we know that is the true PUE? How do we know they haven't connected all the lighting to the power over Ethernet, and it's part of the IT? How do we know they're not using heat banks, load banks inside the data center to try and increase the... it needs to be transparent, doesn't it? And I think maybe that's the energy efficiency directive will help in some respect. But it's going to create a new industry. It's going to create an industry of auditors. Because these guys are going to have to go in and check, okay, you're saying that your PUE is the X, or you are using this much energy, Somebody needs to come in and check that.
Then show me.
Yes. That has to happen. And then once you have auditors, then you need to have a regulatory body to make sure the auditors are truthful as well. And so you build up another big industry around this. It will happen, I think, eventually,
Maybe we'll move away bit by bit from the PUE. One of the OCP panel was regarding how PUE isn't a measurement of sustainability, because two data centers can have exactly the same PUE, yet one is using renewable energy, is doing heat reuse, but that doesn't count in the ratio. Exactly. And even heat reuse actually can increase the PUE.
Yes.
So it doesn't really reflect the sustainability of a data center. So we might have at some point to move away from this measurement to decide whether a data center is sustainable or not.
Yes, I think it's you're right, Natalie. I think it's too, the focus on PUE has been too strong, and I've looked at PUE. I've looked at the history of PUE, and it was originally first proposed in a conference in 2006 by Malone and Belady, and they were working for an IT manufacturer at the time, HP. Mm-hmm. And it was a great argument to take away the focus from the IT and put it onto the envelope, what's wrapped around the IT. And so from that very day, 2006, when it was first introduced, and the Green Grid took it up and said, the first white paper or green paper, is it from the Green Grid?
I think it was Green Grid.
Yeah.
From the Green Grid.
It was from the Green Grid, yeah. And that was one of their first white papers, was the PUE, yeah. But it actually originated from these guys, Belady and Malone. Belady now works for Belady or Belady. I don't know how to pronounce his name. Hopefully he doesn't write to me and tell me I've... but he now works for Microsoft, yeah. So, which he
knows about the PUE a lot.
Yeah, he knows a lot about the PUE, yeah. But actually, if you read the original paper, it says in there, governments will mandate against this metric in the future.
But
in 2006.
2006, meaning the metric didn't change that much, and that's almost 20 years.
It's nearly 20 years, but what it did say, there was a table, it said that a number of data centers with a PUE of 2 was about 10%, and it was ideal, PUE of 2. PUE of 1.6 was the target in 2006. Now you see how far we've come from 2006.
The last metric, the best average that an air-cooled data center PUE could achieve, it was 1.55, if I'm not mistaken.
That's the average for 2022.
For 2022.
But hyperscaler like Microsoft, Google, Meta, they claim a 1.1 PUE. 1.2.
Yeah, 1.1 is...
And then, I guess it will depend also, because you have the mechanical PUE, then you have the standard PUE, then there's several PUEs, and then of course if you also put your label of PUE, it's kind
coming back to what you were saying about also claimed.
Yes, and I think if that's why it's now a standard. So there is what's called the EN 5600 4-2, which is the PUE in the N series, N56, and then there's the ISO 30134. 2, which is the PUE, and it's standard. It tells you exactly how you should measure it, and that's what we should be doing. And it's annualized. I think the problem that we've had with a lot of suppliers to the market, cooling suppliers to the market, is that they quote an instantaneous PUE. So but the problem is that, we know outside temperature fluctuates. It's in the summer,
the whole picture.
You need to have it over 1 year, and that's what will give you a better metric.
An accurate one, no?
A more accurate one, yeah.
And if you're actually working on your IT efficiency, your PUE might be increasing.
It's true, yeah. I mean, we had another project that we ran where we ran an air-cooled data center for nearly 2 years up in the north of Sweden. It's a 500 kilowatt data center in a place called Boden, and we were using direct fresh air, the same as the OCP Meta data center in the north of Sweden as well, and in the US, which uses direct fresh air. We were recirculating the heat inside when it was too cold outside. So you bring in really cold air, you mix it with the heat inside the data center to supply the correct temperature to the IT. And in that situation, we were able to show that if you try and optimize for PUE, you can drop the PUE, but you consume more power.
Yeah. You have to sacrifice.
Yeah, and that's, so you can have these really strange situations where if you should be optimizing for your energy consumption, not for your PUE.
Exactly.
Yeah.
Engineering compromise you were mentioning before. You
Yes.
have to do something.
Yes, engineering is a compromise all the time, isn't it? And for teaching it for 25 years, I've realized that that's what all you're trying to do is give the tools necessary to make the data-driven decisions in compromising.
So
Because if we make decisions based on data, reliable data, then we will make good decisions. But I think all the while we don't have the data, we will make silly decisions, just like governments do. They don't have the data,
with the cloud thing, yeah. So thank you very much. I think it was really enlightening, Jon. Thank you so much for coming, and we appreciate you taking the time and enriching us with all this content, which is amazing.
Thank you so much.
No, thanks for inviting me. It's been a wonderful day here. Yeah, thank you. Yeah.
Thank you.
Thanks for the hospitality as well.
Thank you so much.
Submer, data centers that make sense.